Okay, so today we will continue with we'll start discussing the metric, the concept of metric on the Lie algebra. So this is the chapter 11. Chapter 11. And this, the metric is called Cartan-Killing form. So this is basically metric, a metric. So the notion of distance, how long, that's the metric basically, right? So what we'll do is we'll use the basic feature of the Lie algebra, which is the commutation relation, which is adjoint representation. So we will use the adjoint representation. To construct this metric, to define this metric. So the idea is the following. Let's suppose I am a Lie algebra G, and let's say two arbitrary elements x and y belonging to G. Then we need to define a notion of, say, the inner product between the x and y, right? That is what we're trying to define. So I will always, in the notes, we are using the notation B. B is the metric. B is the scaling form. Right? So B of xy, we want to define something. Now, it should have, certainly a metric has a property that it should be symmetric, right? Right? You remember that if I have a vector x, the usual vector analysis, you have x dot y, this is the inner product between the two, that's the same as y dot x, right? So it should be symmetric. Anyway, let me just define that. So this is nothing else but trace of adjoint of x times adjoint of y. Okay, the trace. So let me just explain this a little bit. Adjoint is a representation, right? And representation is just the only difference compared to other representations is that the vector space on which this acts is the Lie algebra itself, right? Because add x, what it does, add x acting on z is simply x commutated with z, which is again in G, right? X for any z, for z belonging to G, you have add x acting on z. This is the definition. This is how you define add x. So it takes an element in the vector space z to another element in the vector space, which is x commutated with z. So it is acting on the Lie algebra. Okay. So if Lie algebra is, say, d-dimensional, suppose G has dimension d. It's a vector space, so there's a concept of dimension of the vector space. The dimension equal to d. Then you can think of add x as a d by d matrix, right? Because, for example, you can choose a basis. You can choose a basis, just to be explicit. The dimension is d means that you can choose a basis, say ti, let's say, okay, I going from 1 up to d, okay, such that any x belonging to G you can write as x, okay, you can expand the basis. So it's like xi ti, summed over I. Okay? That's what it means, a basis. That you can expand any vector in terms of a linear combination for the basis with some coefficients, xi being numbers. Okay, since we are discussing complex Lie algebra, these numbers can be complex. Okay. That's what you say. So then I can define, so if we want to look at, say, add x acting on, if I know its action on all the ti, then I know the action on all the elements, right? Because any z I can express in terms of linear combination of ti's. So if I know how this acts on the ti, then I know its action on the entire Lie algebra, right? Because this is a linear. This commutation is linear, right? If I can multiply by some number, that number just comes out, right? So it is enough to know how it acts on the basis. Okay. And that I can use. So let's suppose this basis satisfies some relation, commutation relation, with some structure constants, let's say Fi, j, k, tk. Okay, these are the structure constants. There's some constants. So given a basis, of course this depends on the basis. You choose a different basis, the structure constants will change, right? But given a basis, there will be this commutation relation again will be linear combination of the basis. So these are the coefficients. And this is what we call structure constants. It's clearly antisymmetric in I and J. This we have discussed before, right? Okay. So then I can write it like this. This is the same as, okay, let me put something as J here because I'm using the I there. Yeah? So this is the same as Xi, and I just write, so add of Xi, Ti, summed over I, yeah? Repeated index summed over, okay? Maybe I should write explicitly here. Xi, Ti, acting on, sorry, add X on, sorry, this is what I'm saying. No, add X on Ti, Tj is by definition the commutator of this with Tj, right? The commutator of that. Add X. X, I just use the fact that X is that. In general, it will be commutator of X with Tj. Okay? I'm just using that X is written like this. Now use the linearity. I can take out Xi. So it's just Xi summed over I. The commutator of Ti, Tj, which is the same as using this, just Xi, F, I, J, K, Tk. Maybe you're correct. Xi, Ti, yeah, this is correct. That's, so I can. So I'm just trying to motivate. I mean, this is a trace. When you say trace, what do you mean by trace, right? So first of all, I want to show that this is just a matrix. I can write it as a matrix, which you know anyway. This will be some matrix, D by D matrix. I'm just trying to make it more explicit. Okay. So anyway, once you know that this is a D by D matrix, this is also a D by D matrix. It's a product of D by D matrices, and then take the trace. That's what this means. But I'm just trying to make it more explicit, nothing more than that. Okay. You have questions?
You said that B is the metric, right?
Yeah, this is a definition, this point, yeah.
Yeah, it's the definition. And you said that it has to be asymmetric.
Yeah, it is symmetric explicitly here. Trace, cyclic, right?
Yeah, so
you can move this on the other side.
This has nothing to do with the Euclidean geometry, like the inner product of two vectors on the Euclidean geometry. It's
well, I mean, that's what this means, right? I mean, okay, maybe the comparison will become more clear. I mean, in a little while. Once I'm making it more concrete, more explicit, the comparison will become more clear. Okay. So therefore, you see the add X, add X is nothing else but Xi, Fi, Jk. This Jk are the, so what it has done? It has taken Tj, this operator has taken Tj and converted into some linear combination of Tk. Okay. So if I think of this I can think of as a matrix, and in the matrix language, I should write add X and specify what is its column and row, right? So I can specify this, let's say Jk is equal to Xi, Fi, Jk. Because what it does, so when it acts on, or maybe it's other way, maybe it's a minus sign, okay. So let me put it like this, Tj. So if I act on Tj, so this matrix, Jk, Tj, gives you exactly this combination times Tk. That's what this equation is saying. Add X acting on Tj gives you this combination summed over K, Tk. So you see what's happening. This J is a free index, so this is telling you it's acting on Tj, J equal to 1, 2, 3 for each one. Yeah? And this what you get is for each fixed J, I get a linear combination of Tk's. That's exactly the matrix multiplication. So this is the ADX JK, and what we are saying is that this is nothing else but XI FI JK TK. That's what this formula is saying. So you think of, therefore you understand that ADX is a D by D matrix. There is a column and row and column, which each is going from 1 to D. And this is the way, and the action, this commutator action, is nothing else but ordinary matrix multiplication. So if you arrange all the TJs in a one column vector, right, then the action is simply multiplication by this D by D matrix on that column vector.
Your SO3, when we were speaking about SU2 adjoint representation, right? They are just the same.
This, okay, SU2, this is epsilon ijk. But in general, it will be something for any.
But for the case of adjoint of SU2, these matrices become SO3 matrices.
Yeah, but that is not important at this stage. I mean, this has nothing to do with. No, that was just an accident. This will not happen for other.
Of course, but you can think.
Yeah, you can think like that. So, for example, in SU3 case, it will be an 8 by 8 matrix, right? And X will be 8 by 8 matrix because Lie algebra is 8 dimensional, right? So this will be 8 by 8 matrix. SU4 will be 15 by 15 matrix, and so on. Huh?
Right.
Okay, so once you take this matrix and substitute that, put it there. I mean this matrix form, right? So add X, add Y will be say Xi, Fi, Jk. So this is the jth row, kth column. And similarly, Y can also, I can expand in terms of the basis, correct? Just like X, I've expanded. Y also I can expand, perhaps I call the coefficient Y's, I's, or Y, do not use the same index. Let's say YL, FL. And then we'll have, to do the matrix multiplication, so I'll have K and say J prime, okay? This is a D by D matrix whose row is J, K is the column. Here K is the row, J prime is the column. Okay. Maybe I'm confusing unnecessarily because it's probably too easy. I didn't have to say this all these details. Is it clear? This is the matrix. I mean, this matrix whose Jth row, Kth column. Okay. Is that clear? Okay. And similarly, this matrix again. YL, FL, and then again kth row, J prime's column. This is now matrix multiplication. That's why these two are the same. Column here and the row here. But now, if it was simply a matrix multiplication, this is going to give me a D by D matrix with a jth row and J prime column, right? But I have to take the trace. That means I have to set J prime equal to J, and then sum over J. So that's what, very explicitly, that's what we mean by this trace. So then this would say that the result, I mean, I can just open this up a bit more. So from here, we find that Bxy is equal to Xi, say YL, times some, let's call it BIL, where what is BIL? BIL is Fi JK, FL KJ. So the free indices are I and L. I and L are free indices, and these are all summed over. KK, JJ. So purely from the structure constants, you see that you have this is the metric in this basis. And that's what you do here, right? I mean, here, if I have x dot y, what do we mean by that? X dot y. You can expand x in some basis, right? If you have a d-dimensional space, I can choose some basis ei at the basis, I from 1 up to b at the basis in this d-dimensional space. Then I can expand x. X is simply xi, ei. Y is yj, ej. Okay? Or yl, el, let's call it yl, el. then the dot product, the dot product is simply xi yl, and the dot product of ei with ej. Okay, el, sorry, el, and ei with el will be some number, right? Which I call GIL. GIL is a metric component, right? So that's what you do. So xi yl times GIL. GIL, of course, depends on the choice of basis. You choose a different basis, some e primes, you'll get different g's, right? So that's a basis dependent statement. But the metric, the dot product itself is independent of the basis. Okay? When you change the basis, you have, of course, the metric also changes, no? In such a way that dot product remains invariant. The same thing is happening here. Here I have chosen a basis here. In the intermediate step, I have chosen a basis. In this basis, this plays the role of the metric. This plays the role of the GIL. No? In this basis, you choose a different basis, these numbers will change. Okay? So these numbers will change, but also these numbers will change. Because now you are expanding x in a new basis. If I write it as t prime i's, then these numbers are going to change. Right? I mean, in a different basis, it will be t prime I, but then these numbers are going to change, x prime I. No? So both these numbers will change as well as that will change if you go to a new basis, but the total answer is the same. That doesn't depend on the choice of the basis. So this is the basic definition of the metric on the Lie algebra. Okay, is that every point clear? Yeah. I mean, I could have defined this in any representation, right? I could have chosen some different representation. Some R, generally I can write as R of X, R of Y. Right? Again, it's a matrix, the matrix multiplication, and you can take the trace. Now that, in general, the numbers that you will get will not be related to each other. I mean, if I had chosen different representation and compute the same quantity, trace of Rx, Ry, then the numbers you will get will depend on R. In a non-trivial way, in general. But it will turn out that the kinds of algebras we are talking about, we'll be talking about simple algebras. They're called simple algebras. For that, these numbers, this does not depend on the choice of representation. Okay. They are proportional to each other. That's what I'm saying. When I say it does not depend, I mean, okay. So suppose I had computed the same quantity in a different representation, Rx, Ry. So R is a representation. This will be some number, and let me call it this sum. Now this I call dr xy. So it is a representation dependent, because I'm choosing some representation. When I don't put anything, that means adjoint. So that is the original definition of killing Cartan killing form. In general, there is no reason to expect that these two will have any relation. I mean, if the representation is different from adjoint. But it will turn out that the simple Lie algebra, and then we'll prove it, I think maybe we'll, at some point we'll prove it, that for a simple algebra, these guys is going to be proportional to that.
Even if we choose a trivial representation, that we map all matrices to identity.
Yeah, trivial representation is a zero, right? Yes, trivial representation is each other. No, not trivial representation, apart from trivial representation. Yeah. Trivial representation, R of X is zero. So then, no, apart from that, I should say, apart from trivial representation. Yeah. Take any reducible, it has to be a reducible representation, and you know, not a trivial one, because trivial everything is zero. So it will turn out that this is proportional to that, with the proportionality constant being independent of X and Y. That's the important part, right? Because for any choice of X and Y, of course, this is a number. This is a number. So two numbers are proportional to each other. No? But the important point is independent of X and Y.
Maybe the simple algebra does not include trivial representation, or in the definition of the simple algebra.
No. Not trivial. Trivial representation is the one-dimensional representation, where all the x's are mapped to zero.
No, you can't do it. No.
No, no, the simple Lie algebra meaning it has no invariant subalgebra. It has no ideal. Okay. And that it's also not U1. You have to remove U. U1 has no ideal, no proper ideal. No? But U1 is not simple. So apart from U1, everything else which has no proper ideal, that is what's called simple algebra. And semi-simple is the definition. I will come back to these definitions again, semi-simple and simple, in a more detailed way. But from what I discussed yesterday, it was semi-simple was something which had no invariant abelian subalgebra. Okay. No ideal, no abelian ideal. That is the definition. Okay. So is this clear? I hope I have not confused you with unnecessary details. Sometimes giving too much details confuses more, you know. Because here it's already clear. If you are used to thinking about add as a matrix, any representation can be always thought of as a matrix, which is in the same sense. When I say for any representation you can write it as a matrix, it is in the same way. You choose some basis and then and you see what happens with the basis and how it acts on the basis. So if the representation is say n dimensional, then you have n basis vectors. You can choose n basis vectors, and you see how this representation acts on these basis vectors. It will be again some linear combination of the basis vectors, right? So that is going to define to you the matrix, n by n matrix. And this is all this I was just saying to explicitly write down that matrix in terms of structure constants. So the crucial point is that this formula, you see, entirely depends on the structure constants. It's quadratic in structure constants in this particular way. Yeah.
We said that choosing the basis will change the structural constant, so we change the metric.
Yeah.
But the metric tensor.
Yeah.
But the metric itself, the BXY, it doesn't change without.
Yeah, because I mean, if you change the basis, so let's suppose I change from Ti, this basis, to some Ti prime. Then I will have to expand the x in terms of the new basis, right? So if I define the x, now it will be some new coefficients, x prime I, no? Times t prime I. So it is true that the metric will change, okay? Because structure constants will change. So everywhere you put primes, no, prime, because now t prime I, t prime j will be some f prime I, j, k, t, k prime. So everywhere it's all replaced by primes. But so these are also replaced by primes. No? But the whole answer should be independent. It's independent because in this definition I never use the basis. No? Or if you want to do it very explicitly, that changing one basis from other basis is a similar transformation, some so invertible.
Cancels in the.
Yeah, exactly.
Okay.
Yeah. Yeah. So I mean, this you could think of it as in a matrix language, you can write it as, I don't know, X transpose B. B is this matrix, and Y. No.
Yeah.
But then if you change the basis, this will pick up S inverse, Y will pick up S, and this will pick up S inverse like that. So it should work out. It should be basis independent. Okay. This is, of course, I mean, you may say, well, what's the big deal about this particular metric? I mean, I could have, this is a vector space. Lie algebra is a vector space. I can as well just choose any metric. What is so special about it? You see, you want to choose some metric in such a way that if there are certain symmetries, certain automorphisms of the Lie algebra to itself, then the metric better be invariant under this automorphism. You should satisfy some properties like that. And that you can see. So let's just look at that. But before that, before I erase this part, is there any question on this blackboard? Everything is clear, right? Okay, this has an important property that it's invariant under automorphisms of the Lie algebra. So what is automorphism? Automorphism, let's use the same notation. An automorphism let's call it phi. So phi maps Lie algebra to itself in such a way that the Lie bracket structure, of course, it's a vector space, so it's linear map, right? That, of course, goes vector space to vector space. So the structure of the vector space is invariant, is preserved. That is, means addition is preserved. But also, it preserves the bracket. That's the most important thing, Lie bracket. So which means that if I have a phi of, so if I take the commutator of x and y, okay, and take, say, and look at what happens to this. How is this mapped to under phi? That is the same as the phi of x commutator phi of y. Okay? So the picture is something like this. So I have, say, it is a vector space now. Huh? So x is this here, y is here. X is mapped to some phi of x. Okay. Y is mapped to some phi of y. Okay. And now you have an x commutator y, which is some other point. Okay. Some other point in this, again, Lie algebra. This is mapped to some point phi of xy, phi of xy. And the statement here that we are making, the commutator of these two is that, right? This is mapped there, this is mapped there. Then this is mapped to the commutator of these two. That's what it is. Yeah.
Is this also a representation?
This is also a representation, yeah. Yeah, it's also a representation. But now we are talking about very general automorphism.
A new kind of representation, can you say that? The same dimension it has?
It has same dimension, because indeed it's talking about, we are saying Lie algebra to Lie algebra. Same adjoint, yeah, exactly. Yeah. Yeah. But yeah, except that it is, you see, this can be a finite transformations. It's not, doesn't have to be infinitesimal. Phi itself can be a finite transformation. So another one way to think about it is that, you have the adjoint action of the G, the group itself, right? So under the group, X will go to G inverse XG. So this is an example of an automorphism.
So it is like taking some Lie algebra near identity to another point.
Yeah, yeah. No, the Lie algebra itself is a vector space in near the identity anyway. Everything is near the identity.
In the end, it's also near the identity.
Yeah, yeah.
We are
Yes.
always near the identity.
That's right, everywhere, yeah. Okay, and so you want this condition, and also, of course, automorphism also means that this is a one-to-one map, meaning phi inverse exists. Okay. Inverse, you see, in general, if I give you a map, inverse may not exist. No? But this is a one-to-one map. So, inverse may not exist. For example, if, say, several different x's are mapped to the same point, then inverse will not exist, right? So it's a one-to-one map. So every point in this vector space is mapped to a distinct point, different, so that inverse exists. Inverse exists. Phi inverse exists. And such that phi inverse exists. Okay. So now how do we see that this is the case? Well, we can check. So let's see. So if you look at this relation, then what does it say? But this is nothing else. Look at that aside. This is nothing else but phi of add x acting on y, right? This object. This object is simply that. Because this is add x acting on y. But then I can rewrite this as phi add x, phi inverse phi acting on y. I just inserted the phi inverse phi in between. So you should think about all of these things as matrices. Phi is an automorphism which is acting on the Lie algebra. So I can always think of it as a D by D matrix, where D is a dimension of the Lie algebra, right? So this is a D by D matrix, that's a D by D matrix, and this is acting on a D-dimensional vector space. Okay. So now what I did, I inserted a phi inverse phi in between. Everything is a D by D matrix here. So, yeah. So what we are seeing is that this one, so this relation is simply that, right? So phi of add x, let's see what is the statement here. Yeah. Yeah, and so what we actually, going back here, what are we trying to prove? We want to prove it actually, this, right? We want to prove this, that so phi of x commuted with phi of y is phi of xy. That's what we want to prove. But phi of x, so let's try to see what is add of phi of x. Huh? Add phi of x. Let's try to work it out. Add phi x. Add phi x. Acting on any z, let's say. No? So what is that? This, according to this definition, is simply phi x commuted with z. Right? I mean, this is in general. Add of anything acting on z is add of is a commutator of these two things. There's just a definition. But this I can write as phi of x phi inverse z. Correct? Because by using this, the definition of the automorphism, phi of this commutator is the same as a commutator of phi of this with phi of that. But phi inverse is 1. Okay? Is that clear? So therefore this is the same. I mean, maybe repeat that again. So let's use this. Let's use this definition. So why is it so? Let's just check that. Well, this I'm just opening it up, just using this property. So this is the same as phi commutator of phi of x times the commutator of this. So which is phi of phi inverse of z. And here I'm using this property. This is a definition. This is an automorphism which preserves the Lie bracket. I'm just using that definition. But phi inverse of z is z, so you get back that. Huh? So that's why I've rewritten this subject can be written as that. So what does that mean then? This means so add of phi x. So this implies that add of phi x acting on anything, z, is the same as phi. I mean, what is this object? This is nothing else but add x acting on phi inverse z. Right? So that's what it is saying. So therefore we see that add phi x is nothing else but phi add x phi inverse. Because this z is arbitrary. This is true for all z. So this gives you the conclusion that each of these guys, so if I replace this by, so I want to check this, what we want to check is the following. Is it true or not? Add of phi x and add of phi y is the same as trace of add x and y. This is the question, so we want to check that. This is the question, right? Because if we are saying that the metric that I have defined here is invariant and automorphism, this is what I have to prove, right? I have to prove that this is the same as b of phi x, phi y. That's what we want to prove. So there's a question mark here. Is it true or not? Yeah.
But what we are saying here is only valid for the same dimension of different representations. So we can now just say that metric is always the same and the dimension of the representations are the same.
Dimension of the representation, because the adjoint is the same as the dimension of the Lie algebra, right? D by D.
Yeah, because, but we, by phi, we are always meaning an automorphism between the algebra.
Oh, yeah. That's a phi. Phi is an that's a definition. Phi is an automorphism this way. Define G to G, right? Such that phi inverse exists and it preserves the algebra.
I mean, if we change all adjoint representations throughout this proof with an arbitrary R, is it still valid?
Well, it will, I mean, yeah, okay, not this proof, but the way you prove that this is the same for any representation, but that happens only for some simple algebra, for a simple algebra, not doesn't happen for any algebra. No? So far this discussion is for any
this
algebra.
proof is not there yet.
No, that's not there. That proof is done in a totally different way. It is not that. I mean, you have this construction already using adjoint, right? Then you have another construction using any representation, right? Any irreducible representation, not the trivial one, but anything else. And then you prove they're proportional to each other. Okay. But then, of course, after doing that, then since this is automorphism invariant, such automorphism invariant, therefore the other will be also automorphism invariant because they're proportional anyway, right? So this is true. But that happens only for simple algebras, the second step, for any representation.
And among all possible adjoint representations, is this really just one adjoint representation, or can there be different adjoint?
No, there's only one. Because it's defined by the commutation relation. I mean, the algebra.
If we change the basis, or if we use an automorphism to map elements to other elements, then we might get another adjoint representation as we show how it transforms there.
I mean,
it's
you see this automorphism tells me that if I choose a basis, then choose a basis, so then the structure constants will not change, right, with this basis. No, because what this is saying is that phi of, let's say, Ti, Tj, commutator, is the same as phi of phi Ti, phi Tj. Right. But let me call this as T prime I. This is the new basis. T prime I, this I call Tj prime, T prime j. So this is the commutator. And this has some structure constant in general, F prime, etc. But this object is Fijk, Tk, I mean this phi of that, right? But phi is a linear map, so it's the same as Fijk, phi of Tk. So this becomes Tk prime. So you have relation Ti prime, Tj prime commutator is the same structure constants time Tk prime. So if you change the basis by using this automorphism to define your new basis, their structure constants don't change. But that's a very particular choice of basis. No reason why you should choose such a basis. No?
And I guess phi maps from G to G, but phi is not in G, right?
Phi is just arbitrary automorphism. Yeah, it's an arbitrary automorphism. Right. But you see that phi inverse must exist. Huh? So that says that, I mean, in particular, no element should be mapped to 0. You see, if some non-zero element is mapped to 0, the inverse of 0, I mean, it doesn't make sense, right? So there's a whole line is mapped to the 0 because any number times that original object is also mapped to the 0. Okay. So the inverse existence is very important. I mean, it's not, you cannot. Okay. Then, yeah, so what was it, the last point I was saying? I started saying something. Yeah, this point here, right? And so we want to prove that this is invariant. So that's what it means to prove that it's invariant, right? So now can you use that? I mean, can you prove that? So we want to prove that this is equal to that. I mean, this is equal to that. That's what we want to prove. Because this guy is that. But here now, actually there's an exercise, but you can see already, where is that formula? Here, yeah. This formula, look at this formula. This tells you that add of phi x is the same as phi add x phi inverse. Okay, you plug that here, so you get here phi add x phi inverse then again phi add x phi inverse. So phi inverse phi cancels here, and that phi you can bring it here, it cancels, and you get back that. So this is where the trace is playing an important role, right? If you had not the trace, something else, then it would not be the case, no? You can move this around. Cyclicity, basically cyclicity. So that's the important point. I mean, so basically what we are saying is that in this picture, if y is mapped to phi y and x is mapped to phi x, so there is a, let's say there is a notion of distance between that, okay? And this by defined by that. Huh? I mean, distance would be simply, if you want to compute distance, it will be simply bx minus y, comma x minus y, right? That will be the distance. Yeah. Or if you want, we can just look at. So the origin 0 is here. So this is one vector, that's another vector, and I have an inner product defined here. Okay. Now, let's say phi x goes to something else, x goes to something else, let's say phi of x, and y goes to something else, phi of y. Then what this is telling me is that the inner product between these two vectors is also the same as that, the original. So it's or also the distances between the two vectors are the same, 2 points.
Actually, now all automorphisms are allowed to. They must satisfy the commutations, which.
Yeah, that's exactly. So this is what we call automorphism of a Lie algebra. So automorphism of so when you say automorphism of a Lie algebra, it means first of all it's a one-to-one map, and it preserves all the properties of the Lie algebra, like vector space structure or the bracket structure, all these structures.
Even the distance now defined.
Even the
distance between elements.
no, that is the new notion here. I mean, we have defined the distance in such a way that this is preserved under the automorphism. Yeah. If it was not, that would not be very nice. I mean, you want to preserve all the symmetries of the theory. For example, I mean, you have a kind of a rotational symmetry, right? Let's say in the three-dimensional space or a two-dimensional space, right? You want to choose a metric which exhibits rotational symmetry. It's the other way around also usually. Usually you say if you choose if the metric allows rotational symmetry or not, no? But this is the way it is. I mean, if you have a rotational symmetry, for some reason you know that this must have rotational symmetry, right? Then you should choose the metric metric must be something which has rotational symmetry. Or translational symmetry. In the space-time, there is a translational symmetry, right? The space, let's say, translational symmetry. So again, you want to choose a metric which is translational invariant. So it's just that. Okay, this is a very nice property. So to give some examples. So let's say, so remember, given a choice of the basis, I erase that part. So if I choose some basis Ti for the Lie algebra, then DIL was defined as add Ti add TL times trace. I mean a trace of this. Right? This is the BIL coefficient, which I defined. Of course, you change the basis, you get different numbers. That was now. So let's try to construct some examples. I mean, look at some examples where we know SU2. So we can look at SU2 and see what is that BIL. So SU2 was basically generated by sigma i's. SU2 will satisfy the Pauli matrices. And sigma I, sigma j, epsilon I j k equal to I epsilon I j k sigma k. Maybe there's a factor of 2. Yeah. 2 I epsilon. So you can then remember this was written as, I mean, we had an explicit formula Fi, Fl, say j, k, k, j, right? Summed over j and k. So you can use this formula. Structure constants are given here. Okay, maybe I can get rid of this 2. So suppose I choose this as my basis. Sigma by 2 is my basis. Then there is no factor of 2. Okay. So then in this basis, so my Ti in this case is 1/2 sigma I. Then if I choose that, Fijk is just I epsilon jk. So then I see that BIL is I square, so it's a minus, and epsilon ijk, epsilon lkj, summed over j and k. Summed over j and k, this gives you 2, right? 2 delta I. You summed over j and k. So this is plus 2. If you had chosen anti-Hermitian generators, you would have a I. Suppose you had chosen an I there. So this anti-Hermitian generator. Sometimes we use anti-Hermitian generators, right? If you had used anti-Hermitian, then there would be another I for each of them. I mean, so then there will be I here, but there will be no I there, probably a minus. Minus doesn't matter because it's a square. You know? You take the square of that. So overall minus is not important. So, but if there's an I here, then this I disappeared because that's part of the I there. Okay. So then now we'll have I by 2 sigmas. So then it will be without the I here, just epsilon ijk without this minus sign. In that case, you could get a minus sign. But that's just a choice of the Hermitian basis or anti-Hermitian basis. So this is proportional to identity. I mean, this is delta IL, Kronecker delta in this case. Which is what I was telling you. You see, in the fundamental representation, instead of, this was the adjoint representation, right? Suppose I had computed trace in the fundamental representation, R fundamental of Ti and R Tj fundamental. Well, in the fundamental, it is simply the sigma I by 2, right? So in that case, this is simply trace of sigma I by 2, sigma L by 2. L by 2, which is 1/4, and trace sigma I sigma L. It's simply delta IL. This trace is a delta IL times identity, but it's a 2 by 2 identity matrix. So trace is 2. 2 divided by 4 is 1. So you see it's proportional. The delta IL, that's the important part, delta IL. Otherwise, this is just a number. The metric is proportional delta IL. That doesn't change whether it's a joint or whether you use a defining thing, which is in that joint representation, or you had computed this trace in a different representation. For example, this was spin half. If you use some spin J representation, you could have used that. You will get again another number here. This will be J dependent. But that's all. But the delta IL structure will be always there. It will be all proportional delta IL. But that is, I mean, that we will see in general that for simple Lie algebra this is the case, and SU2 is a simple Lie algebra. We will see in general that for simple Lie algebra this is always true.
If this metric has something to do with the space itself, the Lie group itself. For example, SU2 is S3,
Yeah.
and S3 is not flat.
But this is a vector space, a tangent space. This is a tangent space, right? Lie algebra is always a tangent space.
Yeah, it's like evaluating the metric in the tangent space near the integer.
Yeah, correct. Correct.
It's still.
Yeah, so I have not talked about the full group. There is also a concept of metric on the group manifold. Okay, there are. I mean, so let me just give you the basic idea. I mean, we're not going to do anything with that, but I'll just tell you what is the basic idea. the basic idea is actually quite something like this here. So you have, let's say I have the group manifold now here, and here is my identity, okay? And all that we are talking about is the neighborhood of identity, right? This is the Lie algebra. So you look at the tangent space here. No? That is what we are talking about. Now take any other point G, finite group element G. I want to find, so this metric that we have defined is basically the notion of metric in the neighborhood. As you were saying, I mean, if I give you a small distance and a small point, point which is very close to identity, then I can tell you what, this is basically telling you what is the distance between identity and that point, no? That infinitesimally, no? So it's some point here. I mean, I have to draw it a bit bigger. It's all, I'm drawing it bigger because otherwise you will not see it. But it's supposed to be very, very near. Huh? Okay, so this is some point. So this is like, I don't know, e to the power of x, where x is very small, no? So x is, so it's like I'm just going to expand to 1 plus x or something. And look at the distance. Now I want to find what is the notion of metric here. Far away, I mean not near identity, but far away. It's very easy one could do. So let me call this element as h. And this is identity. Well, you take this g and you look at h times g. H times g. Okay? There are two possibilities. I could either multiply from the right or from the left. Just choose one of them. Choose one. Say I multiply by right. Okay. So I multiply this h, I will come here. Now clearly, if h is in the neighborhood of identity, then this hg will be in the neighborhood of g. Right? Because I mean you can easily see. So let's say h, I write it as some e to the power of theta x, theta of x, let's say, theta times x, and theta is infinitesimal. So as so this will be hg will be e to the theta x times g, right? Now I take theta as a parameter. So as you change theta, I'm drawing a curve here, right? So this is, let's say, h of theta. Okay. So as I change theta, I'm going to get different points here. So there is this curve is a one parameter family, one parameter curve, which is defined by theta. And as theta goes to zero limit, this point will come close to identity, arbitrarily close, right? Arbitrarily close as theta goes to zero. Same thing will happen here. This hg, so this gives you a curve, e to the theta xg. So this will be some curve, which is again labeled by theta, right? And as theta goes to zero, this point will come closer and closer to g. Okay. So it's clear that if there's a point in the neighborhood of identity here, this way of writing down, this point h of g is going to be arbitrarily close to g, in the neighborhood of g. Okay. Now here we have a notion of distance. We have defined a notion of distance when this is very, very close. Then we just use the same concept of distance and we declare that the distance here is the same as the distance there. So this is it. But there is a problem here. I mean, this construction depended on whether you multiply by g from the right or from the left. Okay. You could have done the same construction by multiplying from the left. GH may be some other point. Okay? Because it's not commuting. HG is not the same as G of H. These two are in general different points. Right? But nevertheless, this will also be very close to that. Right? But so you could have defined that this distance, I'm magnifying it, actually it's very close. This distance is the same as that distance. Right? So you have two ways you can extend this metric everywhere else. One is what is called left invariant metric, one is called right invariant metric. That's the way you define. So now, a priori there's no relation between the two, but one can prove that for compact groups, these two notions are the same. Okay, you get the same metric, and that is what is. I don't know, there's a name for that metric. But anyway, that is the metric that one uses in the standard. I mean, suppose you have to do some solve some problem, integrations over the full group manifold of some quantity. Suppose you want to compute something like that, no? In that case, you need to know what is the volume form. What is how do you define the volume? Take a small cube or small hypercube near some point. You want to define what is the volume there, no? But the volume is defined like this. Volume can be defined once you know the metric, right? It's just the determinant, square root of determinant of G, G being the metric. So this is the one way to do that. Yeah. Now it's called Haar measure. It's called Haar measure, yeah. In the case when it's a Haar measure. Okay, measure is only, it doesn't need to know the details of the metric. It only talks about the volume form. But once you know the metric, you can obtain the volume form, no? And you get the correct Haar measure, which is invariant. Yeah.
This result says us that locally it's like Euclidean. It's a flat space of.
Well, I mean that now it's not. I mean that's because identity. And now here you see, if I define the notion, the distance, here it will depend on G, right? I mean you are saying, let's say if I have a general metric, let's say how should I? So I mean here you don't see because that's just one point. Question is the statement question whether a metric is dependent on the position, right? That depends on as you change this original point around which you are calculating, right? I mean, even in general, if I have some G of some X, I mean, say some space, you have X mu coordinates are there, and I have some Gx mu, G mu nu, dx mu, right? But this guy can be function of X, right? That's what happens. So you don't see that if you are sitting at one point. Because this discussion is all sitting at one point, identity. So you don't see that. But if you go away, okay, then you will see that this does depend on which position you are expanding around. That's why, in fact, yeah, I forgot to tell you that if you compute if you define the metric like that, you will get the standard S3 metric, round S3 metric. You get exactly the standard metric. But in this course, we never discuss really, we are not focused on the group structure. In this course, we are just looking at the Lie algebra, because that's all you will need in the next semester. I mean, very rarely you need really the group manifold structure, at least not in this course, this 1 year course, you won't really need that. In some cases, I mean, there are models which in quantum field theory discuss, which are like, you have not seen that. How shall I say? You know, when you do quantum field theory, you have not started. Nobody has ever talked about quantum field theory so far, right? Nobody has talked about it. Okay, I mean field theory. I mean, it's basically you are familiar with the classical mechanics, point particle. Let's say harmonic oscillator, right? So harmonic oscillator, you have this x. X is a variable, and you have some action for that, or x dot square plus minus omega square x square, something like that. No, that's the kind of action. But now you can consider where the variable is not just a position, but actually a field, like electromagnetism. You have seen electromagnetism, of course, right? In electromagnetism, what is the action? Is the F mu nu, right? Free electromagnetism. If you have charges, okay, you'll also have coupling to the charge, right? But so imagine it's a free electromagnetic theory. It is simply F mu nu x. So electromagnetism. Action is simply minus 1/4. Okay, this number is not important. F mu nu d4x, right? This is action. Or if you want to write, if you're not familiar with the 4-component notation, it is nothing else but E square minus B square, right? d4x. Electric field, magnetic field square. But these are functions of x, right? X meaning the position. In general, electric field or magnetic field will not be constant. They will be arbitrary functions of position. So it will be. So this is an example of a field theory. But it's of course a very complicated example because the basic variables are the vectors, no? Because F mu nu F mu nu is d mu a nu minus d nu a mu, where this is the gauge potential. It's called, I don't know, maybe, yeah, this is what is we usually call them as a mu as gauge potential. So your basic variables in this theory are a mu x in this theory. And you get the equations of motion, all those things by varying this action with respect to a mu. That's how you get the equation. Or the Maxwell's equation. You get Maxwell's equation from, vacuum Maxwell's equation from this theory. Of course, if you want, you can couple this also to the charged matter. Couple this gauge field with the charged matter, then you will get the full Maxwell's equations, right? So here the variables are a mu. This is of course much more complicated because the variable itself is a vector. The simplest field theories are the ones where the variable is a scalar field. No? Just no index, no Lorentz index. Scalar field. So the simplest theory which you will be studying, actually most of the time in quantum field theory, what you will be studying is a scalar field theory, because that's the simplest one. So the simplest thing is some scalar field, phi of x. Okay? And the action is simply d mu phi square minus half d mu phi square. That's the Lagrange intensity. In some applications, it turns out, I mean, what is phi? What is phi? Phi is a function of x. So it maps, it's a map from x to, say, suppose phi is a real scalar field. So it's a map from x to real line, right? That's what it is, right? Because at each x, this phi of x is some number, some real number, right? So it's a map from the space-time x to a real line. But in some applications, and there are actually quite important examples, where this phi is replaced by, this real line is replaced by the group manifold. Okay. So therefore, in that case, you will write this as the basic variables will be g of x, where g is a group element in some group. It could be SU2, SUN, or whatever, whichever group. And so g is a function of x. So this is what? This is a map from the space to group manifold. These are quite important. I mean, there are very important models, quantum field theories with this. This goes under the name of Wess-Zumino-Witten models, and so on. So in those cases, these are important. I mean, then you need to know the global structure of the group, and they play a very important role. But in this course, we are just focusing on infinitesimal, the algebra only. But your question is, I mean, an important question, of course. Okay. Now, so let's see. Now I have free time. Okay. What can I say now? Good. Now, okay. So let me also write down one more formula. Actually, it is left as an exercise. Exercise 11.1. Okay, but unfortunately, I will need this result for all the immediate arguments. So I will go through the proof of that. But please, when you do the exercise, forget this proof and you do all over again. But I will need this. I will need that result continuously in many cases, situations. So I need to go through that proof. Now, suppose that okay. So I have a Lie algebra. I have a Lie algebra, and let's suppose that I have a Cartan. Okay, Lie algebra, and then the Cartan subalgebra. We'll discuss the Cartan subalgebra in more detail later. But for the moment, you already have an idea, right? We have discussed SU2 and SU3, and we have seen what the Cartan algebras are there, right? So the Cartan subalgebra, let's call it H. Okay. And let's suppose I have two elements, H and H prime, let's say. Two elements belonging to H. So we want to now compute B of H prime. We want to ask, what is this? So, I mean, so how will I do this? Well, I need to, so what is, by definition, there's nothing else but the trace add h prime. That's what it is, right? Now, we already have seen the concept of the, since the h's are in Cartan, you can always diagonalize them, and that is what we call the, in terms of eigenstates, right? The adjoint representation. So we have already seen the roots, root spaces, root vectors. These were the eigenstates, simultaneous eigenstates of all the elements of the Lie algebra. In the SU3 case, we had H1 and H2, two bases of the Cartan subalgebra. And you see, we could diagonalize both of them simultaneously, right? Because they were commuting with each other, so you could diagonalize simultaneously. So you have these root vectors, which we were denoting by x alpha, such that h commuted with the x alpha was a number, but that number, of course, depends on h and, of course, the eigenstate, which eigenstate we're talking about. So that's why we call alpha h x alpha. Right? This was the definition. This was the definition of the roots, right? So these were the roots, and this is the root vector. Okay, and also you know that h with h prime is 0, right? I mean h with any element of the Cartan subalgebra is 0 because they commute. The H is a commuting subalgebra, right? Maximal is the largest commuting subalgebra. Subalgebra of G. The largest. So in SU3 case, we have two-dimensional, SU2 case, one-dimensional, etc. So now, I can, and we also know that add h can be written as a D by D matrix, where D is a dimension of the Lie algebra, right? So let's choose a somewhat clever basis, where we can use all these nice properties that we know of. Okay. So we choose a basis for the matrix. So let's say I choose a basis where the top guy, this is all H. Okay, the top elements are in H, Cartan subalgebra. And then here we have X alpha, X beta, whatever, all the roots, X gamma, all of these roots. I choose. So this will be the root vectors of alpha eigenvalue, X alpha root. This is for the beta root, this is for the gamma root, and so on and so forth. You finish up, you exhaust all of that remaining, right? Because we already know that this is the maximal set. So after that, what we have is all non-zero eigenvectors, right? Non-zero roots. So in this basis, how will the add h look like? So now I want to write add h. H is an arbitrary element of the Cartan subalgebra. First of all, it will be block structure. So I mean, okay. So here I just put 3 of them. So I put three of them here, and 3 of them here. Okay. So this is the space. This is the H itself. This is X alpha space. This is X beta space. X gamma space. So in this blocks structure like that. So here it should be 0, right? Because the Cartan so add h acting on h is 0. On any vector of the Cartan subalgebra is 0. So this part is 0. Here we use this thing, add h. So this is add h. This left-hand side is nothing else but add h acting on x alpha. Okay. So add h acting on x alpha gives you back x alpha. And there's a code, and the eigenvalue is alpha h. So here I'm going to get alpha h. Here I'm going to get beta h. Here I'm going to get gamma h, and so on. And it's all completely block diagonal. I mean, in fact, it's just diagonal, of course. We are diagonalizing. Everything else is 0. Okay. Okay. This was for add h, and similar expression for add h prime, right? So you just put that there and multiply the 2 matrices and take the trace. No? So so similar, there will be add h prime will be the same thing, just replace this by h prime. No? multiply the two matrices and take the trace. So what will be the answer? Answer will be just this sum over. So I don't know, maybe instead of alpha beta, let me put here alpha 1, alpha 2, alpha 3, whatever. I just label them by these numbers. Alpha 1, alpha 2, alpha 3, and whatever. It could be many more, depending on the group, no? It can be many different. So it is simply trace. Trace is nothing else but alpha h, alpha I h, alpha I h prime, something like that. So that's a killing form between two Cartan subalgebra elements. Now in this exercise, there is a 2, factor of 2 there, but that is simply because you have seen that for every positive root there's a negative root also, right? So therefore in this sum is only over the positive roots. Here the sum is over everything, positive and negative roots, right? But if you see, if you just take the minus of this, minus minus is plus. So it just adds up, gives you a factor of 2. So unfortunately in these notes, there are some typos of this type. In some places, it is implied that the sum is only over positive roots. In some places, it's implied that sum is over everything. So you have to be a little careful with that factor of 2. There are some typos here. Okay, so this is rather a very important result. I mean, which will be quite useful for us. Right. Now we come to another important concept. These are and then I will stop. I think this will be the today's lecture. Okay, so we have introduced a metric on the entire algebra, right? And from that metric, if you restrict that metric to just the Cartan subalgebra, it takes a particularly simple form, right? I mean, simple in the sense that if you know the roots, then you can immediately know the answer. Okay. But you can ask the question, what happens to the dual vector space? So Cartan subalgebra is a vector space of whatever dimension. SU3 it was 2-dimensional, right? But then we said the roots were living in the dual vector space, right? The dual vector space. The dual, you can see from the notation here, alpha of h. So this is what? For every h, it gives you some number, right? So it's a map, it's a linear map from the vector space, vector space being Cartan subalgebra, to numbers. And that is the definition of dual vector. So alphas are elements of the dual vector space. So all these alpha I belong to, maybe I should use the same notation actually. So here, the notation, okay, fine. The notation here used is h, this kind of an h, okay? I mean, to distinguish, but it's easier to write like that in the blackboard, so I'll just keep that. So the dual vector space, I'll just put a star here. So this will be the dual vector space. The star means dual. So all these alpha i's belong to dual vector space. Okay, now the question we are asking is the following. I have a notion of metric here. Here, this metric is a notion of metric. Can I construct a natural metric in the dual vector space? That's the question. Is there a metric on this space, which is naturally related to that? Okay. So this is the point here. Now here, so actually what I'm going to do here, this rest of the stuff will make sense only if this metric is non-degenerate. Okay. Otherwise, it will not make sense. Okay. So what does it mean non-degenerate? In fact, I will be focusing on that because that's all we are going to talk about now. From now on. You remember I described choosing some basis Ti. We wrote down explicitly B of Bij, B or Bil, the components we wrote down, and those were simply Fi, Fij, K, and K, L, J, right? That was this coefficient Bil, and if you write B of x, y, where x is some xi, pi, and y is yj, tj, then b of xy was nothing else but xi, yj, bij. Right? That was. Okay. So the assumption here, when we say it's non-degenerate, it means this B, this Bij, which is a D by D matrix, where D is the dimension of the Lie algebra. Huh? So it's a D by D matrix. So the statement is non-degenerate means this is an inverse, or in other words, determinant is not 0. So we are saying dit of this B, of this guy is a D by D matrix, is not equal to 0. That's important. So the inverse exists. Yeah, this is quite important. I mean, in general, I don't know if you have not done, of course, the relativity is, but you know that, have you seen the covariant indices and contravariant indices and so on? Have you seen it? Ah, okay, good. Good. So you know, when you talk about the relation between vector and the dual space and the original vector space is basically that. Say, suppose in the original vector space you define everything with some convention, say covariant index, let's say. Then in the dual vector space is basically everything which is related, which is the contravariant index, right? Because it's clear. I mean, if I have some xi, yi, this is always going to be a number, right? So if I call this guy as a vector, that guy is I call a basis for that is expanded in a basis for the dual vector space. Okay. Now you have also seen, this probably you have not seen, probably this you see only in the GR, I think, general relativity, that if I give you a metric, so I have Gij, Xi, Xj is the length square of this vector x, right? But then this is, let's say this is my vector space, let's say, then this will be the dual vector space, right? Then for the yi, I will define, so yi, yj, gij, that will be the natural length square there, right? But problem is that this is the inverse of that, right? So for this construction to work, you need to assume that this metric is non-degenerate. Inverse exists. Okay? It's the same thing here. So I'm going to assume determinant of B is not equal to 0. B is like the G, the metric. Huh? So I assume that the metric is not 0. And in fact, that's what we'll be dealing with. Huh? One way to define semi-simple Lie algebra, there are two equivalent ways of defining semi-simple Lie algebra. Yesterday I told you semi-simple Lie algebra is the one which has no abelian ideal. Right? One can show that that statement is exactly equivalent to the statement that this metric is not degenerate. Okay? These two there are two ways of defining, which are equivalent ways. And so, therefore, since we are always going to talk about semi-simple or even simple Lie algebras, then for us is always the determinant, the metric will be non-degenerate. Okay? So this is true. And if so, then you can just start from this metric and get to that metric. Not a problem. Just take the inverse, right? To define and that's mainly the idea to this to answer this question. So here I have a metric on the Cartan subalgebra. Can I define a metric on the dual vector space? Okay, that's a question. So the idea is this. What happened to that? Ah, the other thing is disappeared. There was another thing which was nicer. Okay. So I can erase this part here. Okay. So the first step here is that, so we will now assume, that dit of B is not equal to 0. That's we'll assume. So the first step is that you want you want a map. You see, even in this example, we had this xi. Then from xi, I can go to the dual vector space by just lowering the index. Right? So in other words, for every element, so I can define some I don't know, some yi or something like that by just lowering the index, right? So there's a map. There's a map from the vector space element of the vector space to a specific element in the covariant vector space, right? So we want to define that first. So we have these roots, the dual vector elements alpha. To this alpha, I want to associate an element h alpha, a unique element h alpha in the h. So this was an h star. I want to map to a very specific, depending on alpha, a specific element. And the way you would define is the following. This is defined through this equation. Alpha of k is equal to b h alpha k for all k in h. Okay. So h alpha is that element. So h alpha is in h. Is that particular element of h which satisfies this condition. That for every k, this is true. Okay. I mean, in this language, it's like here, right? We have alpha I, ki. Ki is in some basis, I've experimented, and this is going to be a number. But now, what I'm writing here, now both are in the h, right? So both the indices are lower indices. Say j and ki, right? But then I have a gij. This is the metric. So this basically one is saying that alpha I is equal to that. This is exactly the analog of what I was telling you before, by raising and lowering the index, going from the covariant index to contravariant or vice versa. That's exactly what's happening here. So if you have a root, some root which is in the dual vector space, to that root I'm associating a unique element of h which satisfies this property. I mean, this kind of map will always satisfy the property, right? That's why it's important that inverse exists, otherwise this will not go through. So you need to have one-to-one map. So for that, you need the inverses. Okay, so that's the definition. So this is, by the way, the terminology. This is called a root, and this is called co-root. 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 So this is defined by that equation. Okay. Actually, not quite, up to a constant. This constant depends on which Lie algebra you're talking about. It's up to you. I mean, you can choose whatever you want. The final results are not going to be here. I mean, you see, whatever the number is, I can absorb it inside here, because this is linear map, right? This is bilinear. This definition is bilinear, right? It's linear in this first index and linear in second index, bilinear. So in particular, if I multiply by some number here, the number comes out, or you can absorb it in here. It is just that this is for the convenience. You put some number so that you don't get some horrible fractions and so on in your intermediate formulae. There's nothing, no particular reason for that. Okay? But it's just for convenience that you choose some number. Agree, right? I mean, this I can put inside, and I can define this new thing as a new h alpha. No, but this is just used for convenience. Okay.
By k we denoted basis.
Sorry.
K element of alpha. By k we mean basis.
K is arbitrary, but of course, what it means that if you satisfy this for a basis,
It's arbitrary, but they consist of ki's the list of Ks constitutes the basis of.
Yeah, I mean, yeah, you're right. So K is an arbitrary element of H. So of course, if I choose a basis K, I can write always as Ki, Ti. Right? I can always write it that. And then it is enough to, I mean, it's enough to look at H alpha. I mean, it's enough to satisfy this equation for just the basis, whatever your choice of basis is. So this should be true for all K, for all I, right? For all I. If this is so, then obviously it's true for all K.
Like we change indices on the upper examples. For xi from 1 to 3, we can change the indices of the generators from 1 to 3, for example.
Yeah, correct. Yeah. Yeah. So now let us try to look at, just to take some example. Oh, sorry, time. How the time goes so quickly. 1.5 hours to begin with looks a long time, right? But then you find there's no time. Okay, let's just quickly look at some examples. SU2, I will just leave it. SU2 example is very straightforward. So in fact, typically this number CG, which is chosen for convenience, is for the SUN groups, this coefficient CG, SUN group, the algebra groups, this CG, so let me call it CN, N refers to SUN, is chosen as 1/2. No particular reason. I mean, just okay, just for convenience. Okay? We choose that. So let's do. So if I look at now, so for, I mean, okay, SU2 is given there, but let's see. Let's look at SU3. SU2 is trivial. I mean, so let's look at, or is it trivial? I mean, so SU2 is not a big deal, right? Because after all, the Cartan subalgebra is H, one-dimensional. There's a one root alpha, or minus alpha, and so this is telling you that this map is a map from alpha to a particular element in the Cartan subalgebra, H alpha. But Cartan subalgebra is one-dimensional, so this is going to be proportional to H itself. That is not surprising, right? So therefore, that's why it's trivial. So let's look at SU3. So we had two things, H1 and H2. Right? Two. We had chosen, remember the H1, H2, the basis our favorite basis was that, right? That was H1. And H2 was 0, 1, minus 1, 0, 0. Right? The two, H2, H1 and H2. And we had the three roots and their negative roots. So let me just write down the positive root. Positive roots were alpha of AH1 plus BH2 was equal to 2A minus B. Alpha 2 of AH1 plus BH2 was minus A plus 2B. And alpha 3 was the sum of the two. So let me just write alpha 3 BH2 equal to the sum of the two, so A plus B. This was the thing, and they're negative. Right? This was all the roots. So, so in particular, this means I can just write down what is it. So if I look at B, H1, right? I have three quantities I have to compute: B H1, B H1, H2, because it's symmetric. So H2, H1 is the same, H1, H2, or B H2, H2. These are three things I need to find out. So we can, I erase that formula. Oh, that formula which was that exercise problem which you had. The formula was simply the sum over all roots, right? B of H prime to arbitrary elements was alpha I H alpha I H prime summed over I. Right? That was the formula. So we can immediately check. So if I look at H1, so alpha 1 H1 is simply 2, alpha 2 H1 is -1, and alpha 3 H1 is +1, right? So now here we have alpha H1 times alpha H1, sum over all roots, right? So this will be 2 square, so 4. This is -1 square, so +1. And this is again +1 square, which is +1. And then a factor of 2, because I also have negative roots, right? Negative roots are going to give the same number. So this is 12, right? I mean 4 plus 1 plus 1. Similarly, the same thing happens for BH2H2. You get 2 is positive, negative, 1 plus 4 plus 1, you get 12. And this guy, H1, H2, so now you get alpha 1 of H1, which is 2, times alpha 1 of H2, which is -1, right? So you get here, so 2 times -1, so -2, okay? Then alpha 2 of H1, I'm just using this formula. So here take H1 and H2. So this is H1, that's H2. So alpha 2 of H1 times alpha 2 of H2. So this -1 times 2, which is again -2. And here 1 times 1, right? So +1. And again for the positive and negative roots, a factor of 2. So this is minus 3 times 2, -6. So this is the information we have. Good. So we want to now ask. So we want to ask what is. So we want to look at the duals of this, alpha 1 and alpha 2. What is the? I mean the unique element. This element we was talking about. So the alphas will be going to some H alpha, right? This belongs to alpha H star, and this belongs to H, right? So we want to ask what is for alpha 1, which element it is, alpha 2, which element it is. Then of course if you know this thing, alpha 3 you can determine, because the alpha 3 is sum of these two. So H alpha 3 will be the sum of those two. So it's enough to just look at a basis, choose alpha 1 and alpha 2. So we want to ask what is this and what is this. But the defining equation was, what was the defining equation? That B of alpha, what was the relation? B we defined as B alpha K, right? Yeah, so alpha K, alpha of arbitrary element K was B H alpha K, right? With this number Cn. Again, this number is not important, but let's just keep it. Just because you get nice numbers finally, that's all. Alpha K. Okay, so we want to find out for alpha 1 and similar equation for alpha 2. So from these equations, I want to solve for H alpha 1 and H alpha 2, right? But on the other hand, I know that these are elements of the Cartan subalgebra, so I should be able to expand in my basis, right? So in general, H alpha 1, let's first do the calculation for H alpha 1. H alpha 1 will be some combination M times H1 plus N times H2. Okay? I mean this N, M and I don't know, let's say S and T. This need not be integers, and this could be any number. All we are saying is that it's going to be linear combination of H1 and H2. That's all. And these are coefficients. So what is that, this object? So if I plug in here, so I want to compute BH alpha 1, and so it is enough to look at just the basis vectors here, right? It's enough to look at the basis vectors here. Okay, K is any linear combination of H1 and H2. So I need to check. So I have basically two equations. Let's focus on the two equations. I have one equation, alpha 1 of H1 equal to Cn B H alpha 1 H1. and alpha 1 of H2 equal to Cn B H alpha 1 H2. Right? I have to satisfy both these equations simultaneously to fix the H alpha 1. Right? So what is that? So this guy, I now substitute this S and this form. So you get here Cn. Cn, let's look at that. For n equal to 3, it is 6, right? So 1 over 6, the Cn. And then I have S times V H1 H1, but this I know is 12. Huh? Plus T times H2 H1, but that is minus 6. So this is minus 6. That's that. And here, this is again 1 over 6. And this is alpha 1, substituting this, you get S H1 H2, which is minus 6 S. And then 12, H2 H2 is 12. So that's plus 12 T. So this is what you get computing the right hand side. But alpha 1 H1 I already know from here is 2, right? And alpha 1 H2, so I know both of these things from that expression. Alpha 1 of H1 is 2, and alpha 1 of H2 is minus 1. So I have two equations for two unknowns, S and T. Okay? So I have to determine S and T. So you can see, well, if you divide by 6, so you get here 2S minus T, and here you get minus S plus 2T. Right? So what is the, so if you take, the only solution is T equal to 0 and S equal to 1. Because you see T equal to 0, S equal to 1 satisfies this equation. And also it satisfies this. If T equal to 0, S equal to 1, so it's minus 1, it's also minus 1. Okay. So therefore we conclude that S equal to 1 and T equal to 0, so H alpha 1 is simply H1. In fact, this is the reason for choosing that. If you had not chosen the Cn, if you had kept that 1, then you would find this to be 1/6 or 6, I'm not sure. You would find 6. No, 1/6, sorry. Because this 1/6 is not there, so it will be 12S. So 12S equal to 2, so S will be 1/6. So it will look ugly, that's why. You see, you'll put that. No? So to get rid of that, just choose some C. That's all. So this is H alpha 1. H alpha 1 is in fact H1 itself. And similarly, and that is left as an exercise, you should prove, you can prove that also, exactly going through the same steps, you can prove that H alpha 2 is also H2. So both H alpha 1 is that, H1 is this. So this was, yeah. And now finally we are at a stage. So what was the first stage? This stage was to give a map, no? A map from the vector space to the dual vector space, or vice versa. Here I'm giving actually map from dual vector space. Alpha is from the dual vector space, and alpha is from the dual vector space, and we are mapping it to the vector space. Okay. But then once I have given this unique map, then I can define a metric directly on the dual vector space. You see, I can define a metric, let's say alpha beta, right? Because this can be mapped to a specific H alpha, and this can be mapped to H beta, and then I know the notion of distance here. This is B, right? So you can define a notion of distance in the dual vector space by simply using the notion you already have in the vector space, because you have a unique map, no? So it gives you, this is a way of defining it. And then you see from, since there is this relation, then you can immediately see that from this we gather, I have two independent bases for the dual vector space. Alpha 1 is So it's alpha 1. So you get H alpha 1, H alpha 1. But H alpha 1, H alpha 1 is H1, H1. And that you already know. BH1, H1 is 12. Right? There is a Cn also, right? So 12 divided by 6 is 2. Sorry. So alpha 1 is 2. Alpha 2 is also 2. Because this is also 12. H2 is 12. And if you wish, you can also do alpha 3. Alpha 3 is alpha 1 plus. Okay, before that, alpha 1, alpha 2 is the same as 1/6 BH1, H2. But BH1, H2 is -6. So it's -1. And then you can see that alpha 3, which is alpha 1 plus alpha 2. So you'll find that this is also 2 just by using this relation. And all of them. Alpha I, alpha j, when I not equal to j, let's see, there is -1. Yeah, I don't know, we can work out everything. I just write down the answers here. Yeah, alpha 1, alpha 3 is +1, and alpha 2, alpha 3 is +1. So this is what you find. And does this remind you of something? This is exactly the hexagon we drew, right? If you think of, there the length we were taking it to be integers, but if you take the length to be square root of 2, then the length square is 2. So it's exactly that vector that we were drawing. Alpha 1 was this here. There's 60 degrees here, alpha 3, and 120 degrees, alpha 2, and then the negatives. Right? This is exactly that. So lengths are now just root 2. Every length is root 2. Right? And then you see that alpha 1 dot alpha 3 and alpha 2 dot alpha 3 are +1s. So this is just cosine 60 is 1/2. Right? So root 2 times half, which is +1. So that's that. So this is 60 degrees, etc. So you get this picture from here, right? Okay, so this is anyway, the basic logic was this. We have a definition of the metric, the Cartan-Killing form, on the Lie algebra, in the entire Lie algebra. And since Cartan subalgebra is inside the Lie algebra, therefore I also know the notion of this metric on the Cartan subalgebra, right? Then I use the non-degeneracy of the metric. Otherwise, you cannot invert the metric. If it was not degenerate, if it was degenerate, you will not be able to find, you will not be able to solve uniquely these solutions. So there won't be a unique map. No? That is a problem. But if it is non-degenerate, metric is non-degenerate, then inverse exists, and you can give a unique correspondence between the dual vector space and the vector space map from alpha to a particular element H alpha. Then you define the notion of distance in the dual vector space using the notion of distance in the vector space. So this is the chain. That's what it is. Okay. Sorry, this is 20 minutes more. Okay. So we meet tomorrow. Tomorrow is what, Wednesday or Thursday?
Wednesday.
Huh? Wednesday. So we have 4 more lectures, right?
Yeah.
Okay. So I close this.